earthquake struck without warning at 4 minutes past 5 local time. 250 motorists were believed crushed to death on I-80.
Get them out without mega heavy equipment.
Emergency services interrupted news bulletins with appeals for help.
I believe they got a lot of dead bodies up there.
Power out, telephones disrupted, and gas leaking into the air. Fires were inevitable.
Rescue workers say there's still a risk of gas explosions.
The return of the area's perpetual nightmare. A high-tech city perched on the San Andreas Fault.
We have located some bodies, and there are no survivors in the area that was
$2 billion worth of damage.
Seismologists say the big one is probably yet to come.
San Francisco is a beautiful city. People come here from all over the world to live and to visit. But this is earthquake country. And the question is, can science make this a safer place to live?
San Francisco is on the west coast of the United States. It lies at the intersection of two major tectonic plates, the Pacific and the North American. This is the San Andreas Fault, where there's threat of a major earthquake.
The San Andreas Fault runs beneath that lake right behind me. The Pacific Plate and the North American Plate move past each other at about 5 centimeters a year, the same rate that your fingernails grow. But large sections of the fault are stuck because of friction. This causes strain to build up in the rocks for many years, until finally the strain is so great that there's a rupture on the fault. This releases an immense amount of energy that can cause destruction hundreds of kilometers away.
When a fault ruptures, usually many kilometers underground, a massive amount of strain energy is released in the form of seismic waves which shake the earth.
A moderate earthquake rings the earth like a bell. Every single sand grain on the globe dances to the music of that earthquake. A seismologist's tools are simply these, a seismometer, which measures the shaking of the earth in response to that event. Now, if I pop the top off, you can see how simple a tool it really is. By virtue of its inertia, this coil stays fixed. When the ground moves up and down, the frame moves up and down inside the coil. There's a magnet in the frame, and so there's an electric current which changes as this moves up and down. Now, in the ground, we measure not only the motion up and down, which we're most familiar with, but also motion sideways. So there's 3 components of motion. There's the horizontal component here, here, and one vertically. Now we have the complete motion of the earth. We have about 350 of these seismometers in Northern California, and their signals are sent back continuously to our headquarters office. Now let me show you what we see on them. At the top of this screen is a time signal, just so we can keep track of time of the recording. And the middle trace represents our seismic recording, and you can see it's got little wiggles on it, and those little wiggles are noise, traffic noise and wind noise. We can escape some of that by putting the instrument down a well, and in fact that's why it has this cylindrical shape. Now let's create an earthquake on this trace. You can see it come by here. It's got a strong impulse followed by a decay. And the different types of waves stimulated by the earthquake can be distinguished on this trace.
Seismic waves are vibrations in the underground rock. Primary or P waves are longitudinal. As they travel out from the earthquake focus, each segment of rock vibrates parallel to the direction of motion of the waves. Secondary or S waves are transverse. The segments of rock vibrate at right angles to the direction of motion. P and S waves cause very different effects at the ground surface.
It's about 5 o'clock in the afternoon on October 17th, 1989, and I'm parking the car in the marina to go to a place to watch the baseball game, the World Series at Candlestick Park. As I parked my car, I noticed there was someone behind me, not really thinking much of it. As I finished parking my car, all of a sudden, my car just jolted, came to a stop. and I thought that the man behind me had hit me. I got out of my car to look at the damage to the back of my car, but there was no damage, and I couldn't figure it out. Suddenly, people came running out of the buildings, and about 2 seconds later, the earth started shaking. I looked at my car was rocking and rolling. I looked overhead, and I realized I was in a very dangerous situation, and I needed to get under cover. I looked at the buildings, and the buildings were rocking back and forth with rubble coming down. So it was at that point that my friend and I got back into my car.
The first jolt of Marcia McLaren's car was caused by P waves, travelling at speeds of a few kilometres per second. Their effect at the surface is very similar to a sonic boom. S waves are slightly slower, so they arrive a few seconds later, but they cause far greater shaking of the ground.
This map shows the location of my car on the corner of Greenwich and Fillmore, and the little green dot is a location entitled BEA, which is a station put in by the U.S. Geological Survey. It allows us to relate what I felt when I was in my car to what we see in a seismogram. This is the beginning of the earthquake, the P wave. That was when the push-pull sensation that I felt when I felt that the car had been pushed from behind. As this time is passing, about 10 seconds went by when I got out of my car, went to check to see what had happened, and the S wave started, and the earth really started to shake, and the car started to rock and roll. So this distance is about 10 seconds, and that is what we call the S minus P time.
Because we know the velocity difference between the P and the S wave, we can use that information to determine how far an earthquake is from our seismometer, because it shows up as a time lag between the arrival of the P and the S wave on the recording. Now, if we have several seismometers, we can use that to triangulate the position of the earthquake so we can determine its location. And that's how we locate all the earthquakes on the San Andreas Fault here and elsewhere.
There's a rule of thumb that says if you take the S minus P time recorded at a station and multiply that times 8 kilometers per second, that gives you the distance from that station to an earthquake location. Here is San Francisco. I'm going to take S minus P times from these 3 stations and calculate the earthquake location. The S minus P time from this station was 3 seconds. From this station, 6 seconds. And from this station, 6 seconds. Using the rule of thumb, then the distance from this first station is 3 times 8 is 24 kilometers. From this station, 6 times 8, 48 kilometers. And from this station, 6 times 8, 48 kilometers. Where the arcs cross is a reasonable location for this earthquake. A refined location using all of the information from all of the stations actually puts this earthquake about 80 kilometers south of San Francisco and very close to the San Andreas Fault.
Smaller earthquakes happen far more frequently, relieving some of the strain along the San Andreas Fault. But there are gaps with very little seismic activity, where it's likely that enormous strain is building up for the next fault rupture. The 1989 earthquake occurred in one of these gaps, so could it have been predicted?
A year before the Loma Prieta earthquake, the USGS released a report where we evaluated all the faults that created this landscape in Northern California, and we identified the part of the San Andreas near Loma Prieta as the most likely to produce an earthquake. This was just a 30-year forecast, not at all a prediction. Then, 6 months and again 2 months before the Loma Prieta earthquake, there were bursts of seismicity, little earthquakes, but they weren't followed by anything big immediately. Finally, when the Loma Prieta earthquake occurred, we really saw nothing imminent preceding it. After a long autopsy, we can see that there is no strict way to predict these earthquakes, even if we can identify parts of the fault more likely to rupture than others. So if the best we can do is say where earthquakes are more likely to occur, but we can't predict them, the message for all of us who live in this area is to be very prepared for earthquakes.
Most of the casualties of the 1989 earthquake were caused by falling buildings and other structures. Like many older buildings in San Francisco, the Geary Theater suffered major damage. But an understanding of seismic waves allows structures like these to be effectively refitted. P waves from an underground earthquake tend to shake buildings in the vertical direction. This doesn't cause much damage because of the strong vertical pillars which support a building's weight.
Let me demonstrate the behavior of buildings by using this model. The normal loading on buildings is its own dead weight, which loads the building in the vertical direction. Most buildings have substantial strength in this direction. However, most do not have enough strength in the lateral direction.
S waves tend to shake buildings horizontally. Transverse waves like these cause most of the damage during an earthquake.
Horizontal input at the base of the structure, such as that caused by S waves, can greatly amplify the motion at the top of the structure.
Buildings can be made more rigid to withstand horizontal stresses. This is done using cross-bracing or by fitting a so-called shear wall.
As you can see, with the addition of the shear wall, the amplification from the base to the top is greatly reduced. This is exactly what they're doing in the Geary Theater. They're adding strengthening walls. During future earthquakes, this will help prevent people from being injured or killed.
San Francisco's major buildings are being refitted using cross-bracing, shear walls, and other similar measures. But the 1989 earthquake showed that roads and bridges are also at risk unless they're strengthened. Another lesson is that information from seismic stations helps the emergency services to respond more effectively.
Shut off the gas, shut off electricity. Don't expect services for 72 hours.
Pacific Gas and Electric Company is a critical provider of gas and electric services to more than 10 million people here in Central and Northern California. This substation, Metcalf, is one of the important nodes for the interconnection of generation sources of electricity and the 10 million customers who use this electricity on a second-by-second basis. Our goal here at PG&E is to make sure that this service is provided even under extreme conditions. On October 17, 1989, a major earthquake occurred along the San Andreas Fault about 25 kilometers from here, beneath Loma Prieta Peak. The earthquake rupture began at 18 kilometers beneath the ground surface. It took 3 seconds for P waves to propagate up to the ground surface where the jolt of the earthquake was first felt. The S waves followed 2 seconds later and began to do damage in the local area. Up in San Francisco, no one knew what was coming. The World Series game in Candlestick Park was about to start, and everything was normal in PG&E's Energy Control Center. Here at Metcalf, it took about 7 seconds for the P waves to propagate from that starting rupture to the substation here, where the operators in the control building first felt the earthquake. About 12 seconds after the earthquake rupture began, the S waves arrived here at Metcalf and began to do damage to the equipment out in the switchyard. The operators of PG&E's Energy Control Center first knew that something was wrong when their monitoring equipment indicated that power was being disrupted at Metcalf. In 16 seconds, the P waves hit San Francisco, jolting power control into understanding that this was an earthquake. In 21 seconds, the S waves hit San Mateo, another important substation in PG&E's system. The damage that occurred there began a chain of events that led to power being completely lost in San Francisco. In 30 seconds, the S waves hit San Francisco, causing major damage. But by this time, power was already lost. The scientific community collects an enormous amount of earthquake information. We at PG&E can use that information, if we receive it quickly enough, to accurately and effectively respond to earthquakes and restore gas and electric service as fast as we can.
So can San Francisco ever really be safe?
The 1989 earthquake was about 80 kilometers from this point, yet it caused significant damage. The next earthquake is likely to be much closer. Therefore, we need to retrofit our buildings, highway structures, bridges, and other components. We only hope that we have enough time to perform these retrofits before the next earthquake occurs.
We think this region has about a 2 out of 3 chance of another Loma Prieta-sized earthquake during the next 30 years. Now, smaller but still damaging earthquakes are much more likely here. So the message for those of us who live here and work here is we all have to be prepared, because sooner or later we're going to experience something that could be devastating.
I was in Kobe, Japan in January of 1995, just after an earthquake there did extensive damage and killed over 5,000 people. That's an urban area very similar to this one. And that earthquake showed me what an earthquake might do here. But will I go on living